We can't hear you.
Okay, let's hope this works. Okay, for the people online, can you hear me now? Yeah. Okay, wonderful. And I apologize for everyone. All we said is that projects are important. For the people online, can you hear me now? Okay, if someone could like stop giving me back their sound, that would be very helpful. Okay, yeah. Enough. It's very difficult to hear your own past, and we don't need that. No, like, unfortunately, I can't hear you anymore. Chat, we have Anke and Lyle here today, so we will be monitoring the chat with really deep clarity, and we have lots of questions on, lots of comments on chat. So please let us know there. So, what have we learned so far about convnets? We've learned about the nature of convolutions, what is a convolutions, what they're useful for. And at the end of the lecture, I will be quizzing you a lot about all the different ways how the convolution thinking can be useful. We learned about max pooling and what that's useful for. We learned about the training loop for convnets. And for all the convnets and non-convnets, you always need to have like this nice training loop. And we learned a lot about data because that's, it first occurs naturally in the context of convnets. So let's make sure we are all on board for convnets. So suppose we want to find out whether the following image depicts Cartesian axis. What could we do for that? Well, we could convolve it with two filters. If a 3x3 filter, no padding, sprite of 1. And so before I go into this exercise, yes, okay.
My mic is on. Oh, sorry. I should be muted.
Cool. So what we have is we have two convolution kernels. Now, like, why would these convolution kernels be good to ask the question if we see the cardinal axis there? So the idea of convolutions is that we're kind of looking for features. That's at least the motivation often that people have. In which level are those the features for the cardinal axis? Yes. That's right. Yes, but why do we have the minus ones next to it? Minus 1/2.
So you can know that it's finding the boundary between low and high.
Yeah, that's right. No, otherwise, if we're in a homogeneously bright region, it would show us that features. So features will often have this flavor. So now we have a convolution exercise here. We have this thing, and we want to convolve it with this thing on the right-hand side. And I will ask you in the next slide to do this by hand. So start it already. We want to convolve the matrix on the left with the filter that we have on the right. What's going to be the dimensionality of the output of this if I convolve to these two variables? Yes. 2 by 2, exactly. Okay. And now you will all do this 2 by 2 convolution by hand. Why am I doing that? I found in the past that many times our materials weren't good enough and people didn't have an intuition how to do that. Convolutions appear everywhere. You want to be very confident about that. Okay, so and in the next, so you will have 4 variables, A, B, C, D. On the next slide, which is going to be a poll everywhere, I will ask you to put in those 4 variables. Who has the results already? Who doesn't have the results? Okay, do it by hand. Okay. Who has the answers so far? Okay, great. Here's your poll everywhere. What's the result of the ABCD convolution? Okay, wow, we're split half-half. 2, 2, 1, 1. We have a little bit of variance, yes. Great. Okay, so why don't we do it together? Okay, so we have this thing on the left here, multiplied pointwise with what we have on the right. Now that's the first data point that we're going to have. There's 4 zeros, they don't count. We have the 3 zeros in the middle, they all add 1. The 2 ones on the side, they will subtract 1. So the right answer is 2. And there you see the calculation of it at the bottom. Anke. A question in the chat. Wonderful. So this is a question by William Bergstein. William, thanks for asking questions. I want to ask all of you, like always, if anything is unclear, please ask questions. I'm super thankful for that. So why do we want it to add to 0? Would replacing these minus 1/2 with 0 not work? And he's right in a sense. Not like, why are we doing this if the way the world would look like is that we'd get images that only contains ones that look like this with zeros around it. then there's absolutely no reason why we'd want to have the -1/2 over it. But in practice, the features that are good for those problems, now show me the horizontal things, will almost always have like the -1/2 on at the side. Why? Because in the real world, stuff is uniformly illuminated in a way, or locally relatively uniformly illuminated. What that means is if we look at this, at this brightness, all these points will have similar brightness. So if I add something on top of it, yeah, it's going to increase the brightness, but it's going to be on a background of somewhat similar brightness. Now, we will be in some cases where basically everything is super bright. We're outside in the sunshine, lots of photons everywhere. Versus we're inside, and we have this. So the contrast between the bright colors and the dark colors is usually going to be relatively small. These kinds of filters take care of that. And so if you train neural networks to solve vision problems, the filters you get usually have these like side peaks that go into the opposite side. Yes?
So in this vertical filter that you're using, you have a -1, -1. If we say have a different vertical filter, say 1, 0, -1 that we use in C, so would that have an impact on the output of the
yes. No, so if you have 1, 0, -1, okay, let's zoom out a little bit. What are these filters? Arguably, what we have here is an approximation of the second derivative on the x-axis that is invariant along the y-axis locally. Your filter, 1, 0, -1, would be an approximation to the first derivative. So your 1, 0, -1 type filter would basically show me gradients on an image, where it gets brighter or darker in some direction. But you can say an axis is defined as like something bright on black background or something black on bright background. And for that, you're rather looking for the second derivative. But there's computer vision courses that undoubtedly some of you took, which talk about why we would come up with these various filters. No, but like, this is a bridge, if you want, from classical filter design to convolutions, to arguably what we will see if we then train these things. Okay, so this gives us the 2. Now we go here. We have the 1s in the middle, give us just 1 + 1. The 6 ones on the sides will give us -3. So it's going to be -2. Then what do we have down here? The 1s in the middle give us 0. We have 2 -1/2, so it's going to give us -1. And then ultimately here, the 1s in the middle give us a 1. The -1/2 on the side give us nothing. So it's going to be a 1. Okay, that's convolution. So now let's do some max pooling. Now we'll use both filter and we'll use a max pool operation with the kernel 2x2. What's the intuition of max pooling? Why do we do max pooling? Now every convnet does. A lot of convnets do max pooling. Why do we do max pooling? Yes?
reduce dimensionality?
Reduce the dimensionality, yes, that is an important part. No, after max pooling, we have a quarter, if we're in 2-dimensional space, a quarter of the number of channels. What else? What's the intuition? What are we looking for? Yes? That's right. So what we're effectively doing with max pooling is we look for this edge somewhere, but we know that we don't know where exactly that edge is going to be. The output of it is going to be, in a way, the best possible fit of our feature to that. And the intuition, the old intuition was really like, we look basically for little edges, maybe of different orientations in images. And then higher levels will do something with these features. And so it basically says, what's the best place where I can find those filters? It produces a sense of invariance. Now, it means that within this block of 2 by 2, if I take the same input and I move it left or right by just 1 pixel, or up or down by 1 pixel, nothing will change. That is the notion of max pooling. Okay, let's do this now. Now we have 2 filters. We have we have the vertical detector, we have the horizontal detector. Look, we have a horizontal edge at the bottom right. We have a vertical one on the upper left. Now we do a max pooling of those. It means that within this thing, the best fit for a vertical is 2. The best fit of the horizontal is 4. So in that notion, no, and like, don't get me wrong, like in the way how a big convnet works, it's hard to understand it in exactly those terms. But the intuition that we're at least early on driving that we basically look, what's the best fit of this thing that we can find? What's the best thing of this thing that we can find? Oh, look, we find like a good one of these, a good one of these. So this could be the place where the axes cross. Great. Here. So in that sense, convnets are meant to be translation invariant by design. If we have an object occurring at multiple levels, and what we do is we have level for level of max pooling, and it fits just in the right way, and so we don't have to deal with edge effects, then within that range, they're translation invariant by design. So let's talk a little about classical neural networks. And in fact, let's first talk about how the brain is organized. This is the network diagram of the brain. Let's look through that. It's super confusing, so many pieces. But let's look at the pieces. Down there, we have the retina. Then we have the lateral geniculate nucleus. It's part of the thalamus. Everything goes there. And then from there, it goes to higher areas. Okay. Yes. There's a new question here. Great. So this is, again, thank you for Dora Maria Raka, who asked, since we usually have grayscale images from 0 to 1 or 0 to 255, does this affect the feature detection? The example had -2 cent. So, okay, that's a good question. I need to think through that. So if we add a constant to everything and the filter adds up to 0, then nothing happens. So it doesn't matter if I have like -2 to 2 or like 0 to 255. If we didn't have that, it would matter. It would add constants to everything. Now, how much these constants matter is another question. Now, like you could have the constants that are always there then, if we only have positive values, that they're kind of subtracted out at a later point of time. But that would push the computation into a weird range. Now, in the vicinity of 0 is where we have, if we use floats, is where we have our best resolution. So another good reason for why we would want to have like positive and negative values, both for the inputs and for the features. Okay, great. Let's go back to this. Now, and the reason why I'm showing this is it just shows you that the brain is using a non-trivial architecture. Architectures build into systems some notion of some inductive bias, something that like we expect to be seeing. So let's look at that here. Here's the retina. A little bit goes into the superior colliculus, goes to the LGN, goes to primary visual cortex. This in primary visual cortex, oh, this is dead. Okay, in primary visual cortex, you find neurons that look like feature detectors that tell you which angle something has. They also have complex cells, which look like the output of a max pool layer. So the neuron will be very active if it's somewhere, even if you move it within some range. Exactly what you'd expect if it was a linear filter with a max pool outside of it. And then it goes further through the system, like B2 builds more complex things out of that. Then it goes into many parallel streams. Some deal with movement, some deal with where objects are in the world, and some parts deal with basically what an object is, what the identity is, and so on and so forth. So why do we teach you about CNNs? They perform extremely well on computer vision datasets. Everything in a way uses either a convnet or something that does something very similar with a convnet. Yes? Yes, great question. So the question is, if you have convolutions or if you have max pooling, how does backprop work? And let's look at the compute tree. No, like we have an image. Imagine it was just one dimensional. No, like it's the same if it's a multiple dimension. Now, like let's say if we have, let's say it's a vector of length 4, and we do a convolution with filters of length 3. Then basically we have here 2 outputs of that level. Now, like we take in something length 4, we have convolution kernel of size 3. We're going to have 2 of them, and then we might have a max pool. So here's a conv layer. Here we have a max pool layer. We have this. Now, how does gradient descent work? Now, like we will have here, by having propagated it to the entire network, here we will have the derivative of the loss after the max pool layer. Okay, let's call it AN. And then what's the derivative of this? Well, let's think about it. Here we have a max pool layer. Either this one is the maximum or this one is the maximum. What's going to be the derivative for the one that's not the maximum? 0, exactly, because if I change this, now the definition of this is if I change this, how much does this change? But if I'm less than this, then I have no influence at all on that one, and therefore my derivative is 0. The other one's derivative, if I am the max driver for the max pool, what's the derivative of this one? The derivative of M after C. 1, exactly. So the derivative is 1. So the derivative here is still dl over dm. Now, what about this one here? Well, this thing here, this input affects this one. This one affects this one affects this one, but this one doesn't affect it. So the derivative of this one is 0. The derivative of all the others is just the weight that we have in here. Okay, so otherwise from a derivative perspective, it's exactly the same thing. We have a compute tree. Now the compute tree just is of that nature, no? Like that as we go here, from here into the max pool layer, we have pooling size squared the number of units here, of which all but one has no influence whatsoever. So in that sense, the max pool layer is just a selector effectively in how we propagate it back through it. Yes?
There's a question about the parallel with the brain.
Yes.
So at least I think I have a general idea. What is like if you add more layers and parameters to the model than needed, the model can learn that only a subset of parameters used, and others maybe learning something that's like doing the same thing or something else. Does the brain have a similar parallel?
Yes.
The
Okay, so this is a great point. In deep learning, our models are always what's called over-parameterized, almost always. So that means that we basically have more parameters than we have stimuli. Now, like ImageNet, order million stimuli. We might have models with 100 millions, with 1 billion parameters. How does that even make sense? Well, we are over-parameterized. Why does nothing bad happen? Well, that's a big part of the theory, and we covered it on the linear day earlier on. So why being over-parameterized is a good thing. Now let's think about the brain. The brain has 10 to the 12, the brain has 10 to the 10 neurons. No, roughly 85 billion, but 10 to the 10, close enough. We are just doing back of the envelope. Every neuron in the brain in cortex has about on average 7,000 inputs. So that means that we have about 10 to the 15 synapses. Synapses are the connections between neurons. It's the word that neuroscientists use to talk about a weight. How many bits of information about the world do you get in your life? What do you think? How would we approach it? How much supervised information do you get in your life?
maybe a thing about a bit a minute or something, or a piece of information a minute?
A bit a minute, that makes sense. It depends on what you say, what the information is. Now you can say, if it's how often you get reward or not reward, like I only have about a coffee per hour. So you can say that in that sense, Conrad only gets 1 bit per hour. But alternatively, you could be more benevolent and say, maybe we get 1 bit per second. Like while I talk, you get some information, it's not supervised. The amount of supervised information is very small in our lives. In fact, that is also the reason why, as we move on, progressively machine learning moves away from supervised data to self-supervised or unsupervised learning. And we will be covering these things later. Okay, so I like this way of putting it. Let's calculate it with second, because that's for which I have the data in my head. If we have 1 bit per second, who knows how many seconds are there in a year? Well, a year is pi times 10 to the 7 seconds. Why is it pi times 10 to the 7? It makes no sense, but it's a relatively good fit to that. Okay, 10 to the 7 seconds, we live 10 to the 2 years. So we have 10 to the 9 bits of information in our life. No, we have 10 to the 9 seconds in our life, so we will have 10 to the 9 bits of information from the outside world. So the brain massively sits in the overparameterized situation. All the deep learning networks that you think about, they tend to sit in the heavily overparameterized region. It's even more overparameterized than it seems at first, because even if you have more stimuli, you will have lots of stimuli that are very, very, very similar. So you have a region where you might have a lot of data, but outside of that region, you have very little. Great. Okay, I love questions. Any more questions? Let me monitor the chat here. Nope. Okay, great. So let's take MNIST. Do you all know MNIST? Yes.
Well, is there any research into what the optimal percentage of, or like what the optimal amount of overparameterization is there? So 5% of the net should actually be important stuff.
This is a great question, and the optimal amount might be infinity. So there is a domain that we did briefly talk about during the linear time, which is what's called neural tangent kernels. Who has, like, I think it was optional material. Did anyone look into neural tangent kernels? Oh yeah, no one wanted to do theory, so no one did. But like, yes, neural tangent kernels are a way of showing what a neural network would do in the limit where it had an infinite number of newtons. And there are scenarios where you can actually meaningfully formulate what your neural network will do with it. And these things work reasonably well. Now, in that domain, in the kernel domain, you can't really do feature learning. So these aren't generally the best algorithms. But yes, so we don't know what that is. Depending on how you phrase it, it could be somewhere between mildly overparameterized and infinitely overparameterized. Okay, so who knows MNIST? Okay, MNIST is probably the most used data set in machine learning. Lots of images of digits like this. And they're pixelated, and they're 28 by 28 images. Why is it popular in machine learning to talk about MNIST? It's like so boring, lots of sevens.
Wasn't that data set used? I can't remember. It wasn't Alexnet.
Yeah, so Alexnet was on ImageNet already, but LeNet, Jan LeCun's work in that period of time, much of it was solving a commercial problem, which is If you're postal service, you want to scan your images, and you want to detect what the zip code is. Anke. He asked, what's distortion? Okay. Great question. So ImageNet has lots of these characters. 3, 4, 7, and so on and so forth. How should I train with that? Well, the first thing is I can say I use a neural network, I fit it to it, I see how good I am at recognizing things. And that uses the information that I have in my data set, not the 3s and the 4s and the 7s. But here's the idea of data augmentation. Hold on, wasn't there a piece of data augmentation already in the tutorials? That coming only next time? I was pretty sure it was in the tutorial. Did I misremember that? I don't know. We should check it. If it's missing there, I'll be surprised. So let's take the 3. This is a 3 that's actually in my database. But I know that there's certain things that can happen to real-world objects that I know to be irrelevant. For example, if I had drawn the same 3, just a tad bigger, it would still be a 3. I can say, I can build in my human knowledge that if I scale something, make it bigger, it's still the same thing. It should have the same label. So I can take this data set that they have and I can add extra labels. Let's make the 3 big. Let's rotate the 3 a little bit like this. Let's do an elastic deformation where like the top of the 3, and that's what they mean with elastic here, where the top of the 3 is exactly the same, but like I'm squeezing that lower part, make it a little bigger. Great, I have a new data point. So now there's a trade-off, no? How much should I be doing that? How should I be doing that? Why should I be doing that? And let me zoom out a little bit. What I say here seems perfectly computer vision centric. Maybe you're into text. But that same idea equally matters, which is if we have text, I can do certain things to text that should have no effect about the meaning. No? Conrad is talking, Lyle is talking. The only difference is that in one case it's Conrad, in the other case it's Lyle. I expect those to have a very similar meaning. I can augment my data sets by building in such things. The concept of data augmentation is we make our own data. So how far should we go with that? Now, do we just need 1 digit of each kind? No, because there's fundamentally different ways of drawing things. Now, some people do the 7 like this. I learned it in German. I do it like this. Americans write the 1 like this. This is probably how you all write it, but I learned to write the 1 like this. In a data set of millions of users, there will be a few people who learn how to write digits in Germany, and they will do this. So yes, we still want all the data. We want to go do some data augmentation, and that's a trade-off. If we do too little, we have less data. So if we start at basically having no data augmentation, there's no way that a little data augmentation won't help, because it just broadens our data set. We get a lot of extra data points for relatively minor things that are all credible. And like move them up and down, rotate them a little bit. That's all very harmless stuff. What about making it grayscale? Yeah, probably grayscale stuff exists. Probably rotations are good, but how far should we rotate it? 10 degrees, 30 degrees, 80 degrees? Well, like arguably this is no longer a 1. So data augmentation kind of comes with a trade-off of how far we'd be doing this. So this is just a list of many different things of what people did with MNIST. And you can kind of see how convnets are the best approaches to solve MNIST. And coming back to why do we all do MNIST? MNIST is small enough that you can very easily train it on Colab. So MNIST is kind of the size where you can try things, where you can be agile. You can solve it. You can solve it with a suboptimal algorithm. You can solve it with 100 layers. You can solve it with all kinds of different things because it's small and it requires relatively simple models. That's why we all do it. So that's MNIST. MNIST is something that if you want to try things, chances are you will eventually use MNIST if you're in computer vision. Why? Because it's just like very easy to experiment on it because it's so small. I believe about 10,000 images of 28 by 28. Okay, next popular network was then CIFAR 10. Lots of people use CIFAR 10. There's 10 different classes, things like ship, dog, deer. They're color images now. They're still super small. They might equally be 28 by 28, but I don't remember that exactly. Why do people like that? It turns out that MNIST is kind of a slightly suboptimal because it's too easy. So you saw in that table of MNIST results. Now here, linear classifiers already get well more than 90% right. Very simple networks get it like 99% right. So now we're in that domain where we kind of only make 100 mistakes over in our entire data set. It's like we could make the algorithm better by hand coding each of the 100. So it starts to be impossible to basically, you can't publish papers today saying, I'm better at MNIST because at this 0.2 level, like basically it's only a handful of errors. And those, there's then the real risk of overfitting those. So that's probably a question here. What is HAR preprocessing? Does it have anything to do with HAR basis? Yes, it does. And yes, the idea of HAR preprocessing is that you use a wavelet decomposition before going into your networks. Okay. In any case, networks work. CNNs perform quite well on CIFAR 10. From 2010, we get like 80% right. Now we get well more than 90% right. And also keep in mind that if you get into that domain where you're well north of 90%, it's not only that it's unclear and there's a risk of overfitting. It's also that the cases that are left are basically super, super weird. Now, it might be cases where it's like almost like a 7 and almost like a 1, and it really lies in between them. You can't even get supervised data on it anymore, no? Because like, if I ask 10 people to tell me is this a 7 or 1, like half of them might choose 1 versus half of them might choose the other. So in any case, by now, or like by 2016, we were really good at CIFAR 10. And in fact, we were solving harder problems back then. Here's LeNet, just briefly. Classical network developed by Jan LeCun. So Jan LeCun was postdoc of Jeff Hinton's. Jeff Hinton is, if you want, the godfather of the deep learning field. Jan LeCun is not chief AI scientist at Facebook AI researchers. He wrote a white paper that kind of discovered or co-discovered or rediscovered backprop. He founded ICLR, co-founded ICLR. In the old images, he had binary images of 7 by 12. That's how things started. The postal office had it. And the architecture of LeNet was you take the input, you take feature maps that 6 different features, basically simple, which ultimately is simple edges, then max pool 2 by 2. Now we go from 28 to 14. Then he has 16 features of 10 by 10. And then max pool going to 5 by 5. Now he has 16 of them. And then he has multiple layers of fully connected outputs with Gaussian connections. They had a lot of like handcrafted pieces of that. And his network had 60,000 parameters. So today, many models will contain well more than 1,000 times that many parameters. Back then, it was state of the art. Back then, training it apparently wasn't all that easy. And I remember at the old conferences, how Jan he had like this old little webcam like 20 years ago, and he would point it at something. It was like the next model. He would point it and he would say, human input, like a square on your face. And like these demos back then were just so cool. Today, any one of you can like code like face detection up as a small part of a research of like just a class project. In any case, by then, he was better than what people had. Later, they used support vector machines to actually be as good as Jan LeCun back then. They used support vector machines, which of course made it relatively slow. So I believe that for LeNet, there were real commercial applications back then. Just briefly, LeNet, how to implement it in Pytorch. It's like literally today, it's 13 lines. No? Like what do we have? We set up 2 layers of convnets, 3 layers of fully connected ones. And then with an output with a relo, with a max pool, another relo, another max pool, another relo, and then it produces the output. And then you just train it and it will work on it. Alexnet, developed by Alex Krzyzewski. In a way, when Alexnet came, that was the year where everyone started talking about convnets. Everyone started talking about deep learning. Weirdly, Jan LeCun had been doing successful deep learning for a long time, but it felt very niche. Whereas Alexnet, not like you have images like that, and it will say monkey. And who built it? Alex Krzyzewski built it with Ilya Sutskever and Jeff Hinton. And Ilya is now chief scientist, or back when I made this slide, chief scientist as OpenAI, inventor of sequence-to-sequence learning, major impact on text field. Yes?
To me, it seems like max pooling is losing every 5% of each kernel. Is it like negligible for every layer, or?
It loses what? Oh yeah, it loses so many. Yes. So max pool in a way gets rid of spatial resolution, or like I take these 4 filters and I just report what's the best one. And it naturally reports from that feature detection, results from the feature detection way of thinking about things. But it loses information. And it's not clear that it should be like that. Not like, so now why is it that we say it doesn't matter where it is? There are cases where it matters. Now, if I take like one of your eyes and I move one up slightly relative to the other, it would matter greatly for certain tasks, like symmetry detection or something. Now, like, there exist newer versions. So slowly convnets have been, so slowly max pool has been losing in attractivity. So a lot of people now don't use it. They use more sophisticated version and say transformers can be seen as if it was a convnet, only that it can be much more, in a way, precise and use more precise relationships between things. So, in any case, Alexnet was on ImageNet. Fei-Fei Li produced the data set, 14 million images, more than 20,000 categories, things like strawberry and balloon. No one uses the 20,000, almost no one uses those 20,000 categories. There's a subset of, I believe, 1,000 categories than most people use. And that contains things like DAC sound. So it's still a rich visual world. It's not a world which contains absolutely everything. It will contain strawberry, but there's just some categories that are very, very rare. So Alexnet's architecture is kind of super funny if you think about it. You take an image. Now you have 2 convnets running on the image, the top one and the bottom one. They both have some convolutions. They have big, by today's standards, very big filters, 11 by 11 go into it. So they have, at the top level, they have 11 by 11 kernels. And then they have these 2 things. Then they have a max pooling. and another convolution, and another max pooling, and another another convolution, and then another max pooling, and then 2 layers of fully connected at the end. Why are there two systems in parallel? Look here. The top one touches the bottom one only at one place, at like this third layer, where those things can have convolutions that depend on both. And then it only again touches the other one all the way at the output. Well, why? What do you think? There's 2 convnets that just like briefly talk with one another. Why would anyone in their right mind have that idea? Well, okay, let's think about what's going on here. So this was the time where graphics cards were new. They had 2 graphics cards in the machine. Moving data from one graphics card to the other graphics cards is slow. So what they did is they built 2 convnets in parallel, one for each graphics card because they could. And then they give only very weak connections between them because like they just can't get, they would be much slower if they did it otherwise. So they, in a way, built the network that they used around the hardware that they had. They had 2 nice graphics cards in it. Why did they need 2 graphics cards? Well, it turns out that one graphics card wouldn't have had enough memory to store all those weights. So they were trying to put in the biggest thing that would fit into the graphics card. And in a way, they were, so the strength of Alexnet, in a way, is that these people who had always believed in neural networks were meeting the people that were really into engineering. So they were like, okay, we have this hardware. What is the maximum that we can get out of this hardware? And they used it very effectively. Great. So Alexnet smoked the competition with 15% top 5 error. By today's standards, that's absolutely horrendous. But the runner-up had 26%. So there you had these people using like classical machine learning on it. Neural networks, they were looking down on neural networks, and in comes this group of neural networks people who completely destroyed it. And so this is why it had so much of an influence. One of the first neural networks trained on GPUs was Qt. Should be mentioned though, there had been 4 previous contest-winning convnets. So it wasn't the first one. It was just the first one where they felt like, oh my God, like, yes, this is like, and why was that so much better than previous convnets? Well, because these guys were really engineering to get most of the, get really the most out of the GPUs that they had. They trained with 60 million parameters, been cited over 30,000 times, and there's the link. How do we use Alexnet in Pytorch? Well, import torch vision.models as models, and Alexnet is models.alexnet. So it's basically 2 lines to have Alexnet. Lots of people use Alexnet or like one of the other early ones because they run very fast. They were meant to run on really cheap hardware. No, they were meant to run on what today is exceptionally cheap hardware. Back then, this was a really cool machine. But that means that it's a relatively small model, no 60 million parameters. It's no problem. Like it will fit into any graphics cards that you can realistically get a hold of. And it makes it very easy to check things. And like, what if we retrain Alexnet? What if we give Alexnet like a different transfer function? Like it's relatively easy to play with these things. Again, here's the source code, super short. VGG is the next one that came then after Alexnet, developed by the Visual Geometry group. And they had one goal for their project, which is beat Alexnet. And they did. They went from these big convolutions. Now, Alexnet had 11 by 11 convolutions in the beginning. So they were looking at really big things. Whereas then later they used smaller ones. 3 by 3, and another 3 by 3. So what's the advantage of having lots of small convolutions versus one big convolution? If I want 11 by 11, I could either, well, have 11 by 11, which we, or I could have like multiple layers, like 6 layers or something of 3 by 3. Why would I want to do that as opposed to the big convolutions? Yeah, there might be local features. The other one is, of course, it requires far fewer parameters in a way. That's 3 by 3, it's tiny. And then they had 64 features here, 128 features here. So look, they have far more features than Alexnet had. But they basically build the filter by lots of convolutions that are stacked on top of one another. 138 million parameters. The whole network is way bigger than Alexnet. Where did we have that here? Somewhere we had the number of parameters. In any case, something like factor 10 more parameters than Alexnet, if I remember it. Actually, it's going to come. Again, how do we use it in Pytorch? Well, we can just trivially download it. And then Google improved things a little further. What's the idea? They use Inception modules. And an Inception model says, well, look, in VGG, they use 3 by 3 convolutions, but do we know that 3 by 3 is the right ones? Well, we could do a 3 by 3 or a pooling with 1 by 1 or a 5 by 5. Why not all of them? Why not all of them is one of the big ideas in deep learning. Getting an extra idea into your network will usually buy you a tiny bit. So they kind of had like the 5 by 5, the 3 by 3, the 1 by 1, giving them lots of hyperparameters that they can optimize, which made performance a little better. In section version 3, they just changed it from 5 by 5, which requires you 25 parameters, to 2 stages of 3 by 3, which requires you 9 plus 9, which again benefits a little bit. And by that time, they were at 6.6% top 5 error rate. Does everyone know what's top 5 error rate? Okay, so I asked the network, not just tell me what is this. I asked the network, give me your guesses on it. Network will be like, most likely this is a hand, but second likely it could be a stop sign, third likely, and so forth. So by using top 5, it's fine if it's one of them. Why does that matter? Some things that might be labeled dark, others might be labeled dachshund. Every dachshund is also a dark. So in some cases, no, or you can say this thing, it's a hand, but it's also a human being. What do I mean? Well, maybe both, maybe one of them. So top 5 error rate kind of makes this be more benevolent for the networks, if you want. So here's a cool graph that in a way shows what was happening in early computer vision research. On the y-axis, that's hard to see here, let me fix that. On the y-axis, we have how many operations it takes to train the network. The size of the circles, how many parameters it has. Big circles, lots of parameters. And here you have the top 1 accuracy, which is how often it says exactly the right thing. Top 5 accuracy is the same thing, just shifted further up in a way. And so what do we actually want? Arguably, we want small models that are cheap to train that still work really well, which is what we'd find in this area here. Look, VGG, they were huge. They had 155 million parameters to solve a relatively easy task, which is ImageNet classification. And then you can see here's in a way like an efficiency frontier. It's probably not the final efficiency frontier, but you can see there's lots of networks. They have the ones that are on the frontier have relatively small number of parameters. They require relatively, they are the best for a given compute. And you can see these big networks with lots of parameters, they kind of don't seem to lie on the frontier. And that's arguably what you want to expect, because they basically have more parameters than necessary. And you can see, Alexnet here still required a lot of operations to train. MobileNet v2. Like among a lot of people playing with networks these days, they then like taking these small, easy to train networks because they have far fewer parameters and it's much faster to try things. And this graph, I'm just such a huge fan of this graph. It just shows like this whole old history of convnets in one graph that I think really tells us why things are happening the way they are. You can see mobile, and you can easily see why like MobileNet v2 and FD MobileNet are really popular. They're tiny and they're fast to train. How do they work? They basically use extra tricks, extra assumptions about the world, the way the visual world works. Whereas VGG, this was just, let's give it lots and lots and lots of parameters and it works, but like it's just, it didn't have many other ideas. But applications. No, it's used for image recognition. Convnets are used for style transfer. You've probably seen those. You take a photo and you're like, this Gattis et al. You say, well, give me that photo in the style of this. What do I mean with style? Style is something about local properties of images. And in that case, the local co-occurrence statistic is everything is blue and everything is kind of in terms of like brush strokes. Makes that photo into something looking like this. Or give me that photo in the style of der Schrei. And so on and so forth. Beautiful. And it's all based on convnets. Just to show you an example of maybe something more modern that is maybe more usable, here we have a UNet that's used for segmentation. As input, you have an image. In biology, we often have that looking like this. As output, you want a segmentation looking like this. And what you do is you have convolutions and pooling, and convolutions and pooling and convolutions and pooling and convolution and pooling. But then in the end, you want to go the other direction. You want to go back to draw an image where you draw the segmented results. And so what they discovered there is that giving them also, now you can say, how do I go now that I have low resolution and segmentation? How do I go back to higher resolution? Well, I do an upsampling and I also give the original image. And then we have convolutions here and so on and so forth. So what's the insights of UNet? We do an up convolution, fixes the problem of shrinking images. Now, convnet always makes them smaller as we get to the pooling layers. An example of fully convolutional networks. It goes from the input pixels all the way to the output of pixels. All it does in between is basically have pool layers and have the opposite of pool layers where you kind of sample up. It allows for resampling of the upsamples by long rates and goes along with decreasing the number of feature channels, not the same as deconvolution. There's 3D convolution that is extensively used in lots of areas now for videos. Convolutions are used for speech recognition. And in lots of cases, they're actually competitive with recurrent neural networks. Input layer there is basically frequency by time, the spectrogram. We have convolutions there, we have max pooling there, ultimately allows good performance on some speech recognition tasks. Graph convolutions, we almost added a day on graph convolutions to the course. It still seems that it's not used so often that it's worth going all the way in there. But the idea is, in convolution, what I do is I apply something here to the image, I apply something there, I take whatever is better, wherever I get the best fit. I can do similar things on graphs. No? I apply something you and your friends, and I calculate something. I calculate something you and your friends cover something. I know that you know one another, and therefore by virtue of you knowing one another, there's probably something that I can learn about you by knowing about you, and I can propagate that information. So in that sense, it's the same idea. Now, briefly, myth convnets are only for computer vision and RNNs are for NLP. I know a lot of you are interested in text. learning structured text representation. Here's like cases where convnets, at least until recently, were state of the art for an NLP task. Now, let me say one more thing. The things that happen in the last very few years, in many cases, it's not great for a project because the projects from the last few years, they probably threw a lot of, that are state of the art, they probably threw a lot of compute at it. In fact, the compute used per deep learning project for state of the art has been rising at a crazy pace. So chances are that the 2021 paper, you can't get it to run, whereas the 2017 paper, you can get it to run. So I just want you to be aware that in many cases, convnets are still useful. Now, at the same time, let's talk about the downsides of convnets. Now, like, arguably, they solve the wrong problem. We don't want invariance. We don't want that, like, maybe if you look at my eyes, that it doesn't matter where my eyes are. My facial expression would be different if my eyes kind of like, or at least my eyebrows. No? You can say, if you have an eyebrow detector and you want to do emotion recognition, it makes a big difference if I look at you like this or like this. Getting rid of like that fine spatial information is arguably a mistake. And in any case, we want equivariance, not invariance. It's a bad fit to the psychology for shape perception. It's a great question. What is equivariance? Now, invariance means that if I shift something, nothing happens. Equivariance means that if I shift things, the same thing happens to all of them. Why? Do you have a better description? Everyone's frowning at me. If I was invariant, I couldn't detect that, but I did detect that.
So I think you need concrete examples of it.
Okay, that's great. So let's draw a concrete example.
Those like hand
There was a hand up, yes.
Is what you're saying here that like location doesn't matter? So like you switch the eye and the mouth, it would return.
Yeah, so let's be clear about that. If I want to tell you this is a hand, then within a range where the hand is, doesn't matter to solve the problem of where's the hand. But now if we want to say, where's the hand based on maybe you detecting fingers, then it does matter, like what is the hand based on where the fingers? It does matter. And let me draw an example here. The face. You have two eyes and you have the mouth here. That face is not identical to this face. They express something very different. If you have an invariant filter, which basically says, I detect that filter somewhere on the image, I detect this filter somewhere on the image, I detect this thing somewhere on the image, and they're fully, not like take the pooling, the max pool layers over the entire image. In that case, these two are exactly identical. Like they both detect the same three features. They just don't carry them over. So you have like, in the case of invariant filters, you can't detect like basically a Picasso. The Picasso is just same features, but at a slightly different spatial configuration. Now, in reality, convnets don't quite engender invariance because the way they work is they put it together step by step. So, and on top of it, there's edge effects. So you never really have invariance there. So convnets are somewhat in between, and that's why I say that they're messy. They aren't quite invariant, and they aren't quite equivariant either. They're somewhere in between. Now you can say what I'd want is that any translation of the overall thing has no effect, but any change of the configuration has an effect. It's important. It's meaningful about the faces. It also doesn't use like aspects of the structure of the world. That basically, if I have images and I move them, there's something very predictable about them. And And in general, max pooling is a problem. Not translation invariance is the wrong problem, the Picasso problem. Convolutional neural network detect parts with no sense of the whole. Now, it's not entirely the case. Not like because you can use the edge effects, a neural network can distinguish between Picassos and the outside world. But it's basically, the max pooling is kind of kludgy. It's kind of a hack. Which is also interesting. Like the linear weighing for the filter is learned, but the max pool is not learned. So the history of machine learning is always if we take something that is not learned and we replace it, if we take something that's designed by a human and we replace it with something that is learned, we always do better. So the max pooling appears like an opportunity to do something better. It doesn't use properly the structure of motion, and it does not account for the offset in its computation. So it kind of doesn't use where things are. It does ensure in a way that information about localization is erased, which is not good because we use it. So here's what Jeff Hinton says about it. He says it much better than I ever could. He says the pooling operation used in convolutional network is a big mistake. And the fact that it works so well is a disaster. And it is not like the max pooling sort of like seems logically nonsensical. Why would it be the case that it doesn't matter where two features are? No, it's not true. If you allow me an image and locally reshuffle it, it's not going to look like anything at all. So in any case, what might be a superior architecture? We would like to have good priors. Things like an ontology, like the world is made out of objects that have properties. And there's classes of them, and there's subclasses of them. You can say inverse graphics. Objects move linearly in space, translation, they do rotate. Information should be routed to the appropriate neurons. But you can say it's not about size, it's about agreement. And like if multiple neurons talk about different aspects of an image, you'd want them to, agree. Yes?
And point of inverse graphics, are there any architectures that have been trying to throw sort of rotation matrices in? Sort of with parameterized rotation matrices? Yes,
there exists a rich literature of models doing that. And I should say, Jeff Hinton gives his answer to this. It's called Capsule Networks. It didn't work. That being said, there's kind of things that are true about the world that we aren't using. And convnets are kind of a hack that seems to work well enough for most cases. And we have a relatively poor understanding of why convnets work so well. Now, like Jeff Hinton is like, yeah, convnets, like the max pooling, it doesn't make any sense. But he's not, okay, and here's why it actually works. And that's very hard to interpret. No, we'd like our networks to be interpretable. We'd like to learn from very few examples. Humans, I can show you a new object. You'll learn it immediately. It's very hard to do that. And it should be better, and it should run fast, and so forth. And what do we today? We mostly do transformer architectures. Transformer architectures seem to work well in those cases where convnets have been working well. Arguably, they are less arbitrary, although that can be entirely discussed. But they also don't carry what we know about the visual world. Now, like, in a way, we're in a bizarre situation. We have a whole bunch of algorithms that work really well. And we live in a world where we know things about the world. As data scientists, we know that the right way to organize algorithms is to build in what we know about the world and make our algorithm be a result of what we know about the world. But that's not why we use convnets. We use convnets because they work, and they're like very weakly driven by the idea that the world is translation, which isn't quite right. And you'll hear about that. So let's briefly talk about one of the heroes in that area. Here you see Jeff Hinton, English-Canadian cognitive psychologist and computer scientist. Like a lot of people in deep learning, he came at it in a way of wanting to understand intelligence and wanting to understand brains. And he did one innovation after the other that really drove the deep learning field forward, not because he wanted to necessarily that to work so well, but because it was his way of trying to understand brains. Popularized backpropagation. It's been called the godfather of deep learning, co-invented Boltzmann machines, which are statistic generative models, contributed to Alexnet. No, he was like the last author on it. In fact, if you read the Alexnet paper carefully, you see that someone on the team and people all point into Jeff Hinton's direction, wanted to build more biological inspiration into that. Whereas his team then ultimately just wanted it to work really well. And there's like a few funny disclaimers about that. He advised Jan LeCun, Elias Sutskever, Radford Neal, Brendan Frey, so many of the big people in the machine learning field now. And he created many of the networks we enjoy these days. So let's do a little bit of convolution thinking in the last few minutes what we have. What's a convolution? Yes. That's right, yeah. We take a kernel that we use locally to extract something from that. And why do we use it? Now, there's a commitment to why is it that we're using small kernels, apply it to things. Yes. Yeah, like it's in a way, convolutions are a commitment to local features that we can look everywhere, and we're basically looking for this needle in the haystack, something locally that tells us what's going on there. And that through learning, we can get better at that. Now, you've seen convnets applied to images. Now, what would you do if every pixel was different? Now, we take the same camera, but every pixel has its own gain. Now, like what they report is not brightness. They report brightness multiplied with some constant. What would you do then? Yeah? Sorry? Yeah, you'd want to get rid of that. Now, like, because to apply the convolutions meaningfully, you need that everything locally is the same, that the meaning of every reading of the inputs is the same. So you'd need to normalize it. So what would you do if I give you a camera, has the same pixel that your regular smartphone camera has here, smartphone, but someone just shuffled all your pixels. No, so you don't know which one is which. My photo camera takes 1,000 by 1,000 images, and they've just been randomly re-indexed. And it could sketch how that could come about. I'm a hardware manufacturer. I have lots of wires from every camera pixel. I have one wire come out. It was 1 million wires. I didn't hire like a good solderer for it, but I basically take these 1 million wires and I jam them into a connector so that they're all connected to a digital to analog converter. What would you do? And you want to do the same thing. You want to recognize cats versus dogs. Yes. Yeah, you'd want to run convolutions because they work well. So,
but if the image is shuffled, there's no relationship between one
That's right. So how would we solve that? We'd want to unshuffle it, no? How would you unshuffle it? Data science riddle. Super useful, important for privacy of patient, weirdly, that problem. Give you those 1 million channels. I tell you it is a 1,000 by 1,000 image. How would you know how to unshuffle them? No, I don't give you original images. You can use anything you want in it. Well, not color, no? Like every pixel detects red color. So we will have like 3 different pixels at 100, 100 red. No, I will have 1 at 100, 100 red, 1 at 100, 100 blue. So we'll have 3 million pixels. No, let's take out color. Let me make the problem easier. There's no color, just 1 million brightness images. But you're right, yeah, we can use brightness and contrast. But how would we use it? Yeah. That's right. Not only that, but if we have lots of images, we can say across all of them, if we are neighbors, then the probability, then we will be very much correlated in real world images. If we're far away, we won't. So what you can do is you can calculate the correlations between neighboring pixels. If you're close, the correlation will be high. If you're not close, the correlation will be small. And then we can embed them into a 2-dimensional space. What's the algorithm we'd use for that? Okay, so who knows Isomap? Okay, Isomap is a dimensionality reduction technique. Works like this. Take every data point. I take the most similar ones. That could be like maybe my 6 or 8 or 10 neighbors or something. And then you kind of build that thing between the pixels. And then you say, now I want something that basically makes it so that the distance in space is the distance that I travel through the network that I produce. There's a few extra tricks to it. It's a classical data science dimensionality reduction technique. Okay, and with that, we can now embed the things into 2-dimensional space. And then we use the same convnet that we use otherwise. So what would you do if there's no spatial organization at all? No, every pixel just tells you something totally different about the world. Would you use a convnet? No, you'd have to go back, fully connected network, or use classical machine learning. Let's talk about what you do if you had graph structure. And there's the field of graph neural networks, but I want you to think about what it would mean. The world has underlying graph structure. Say I had the friendship network of the students at UPenn. And I want to ask who I should recruit as TAs for my next deep learning course or something like that. How would I use convolution here? What's the notion of convolution? That's good. Yeah.
We represent the graph in matrix form and the column. Like with what's the one where like each column represents the user and then it's 1 or 0.
Yeah, I can use a binary matrix to say who's friends with one another. Yeah, like I can often represent graphs as matrices. In this case, I could. But how would I now use convolutions there?
I guess you'd have to use larger. The issues that, like, I guess where the people are sort of arbitrary, like arbitrary columns is. So you have to shuffle all. Maybe you have to shuffle the columns randomly.
Okay.
And then train different samples, we're calling we're all shuffled normally.
Yeah, but alternatively, no, I can say, what is it that I expect to be invariant? No, when it comes to images, I can say moving something is irrelevant. Now I can say the same thing is true in a network, where if I have a feature that's kind of like the goodness of TAs, or like you are like the kind of person who's friends with people who would be good TAs. That's local information, and I expect that there's something going to be invariant about it, which is there's going to be invariant patterns that make someone maybe be a good candidate. In that case, I want to locally extract things from the network.
Would you make like a graphical representation of dimensional space? So make it like n dimensional for n number of people, and then the distance, make the distance between them physically the actual visual distance between the user, between the people.
I can, yeah. That would be the equivalent of distance in space. Now, that's the equivalent of the convolution kernel, how far I want to go. Now, and you can say, how far do I want to go in a network? Well, what I know about you might be important, but what I know about your friends might be important. Maybe what I know about your friends' friends will be important, probably not beyond that. So that will tell you about like convolution sizes that I'm looking for. And last question, what would you do if you had like crazy input sensors, say lasers? I mean, this world where I have lots of lasers pointing into random directions, and they report where they hit a target. Now, so I'm in a room like this. I have lots of randomly pointing sensors from the outsides. I want to recognize that there's a person sitting there based on these laser sensors. What would I do there? Yeah, that would be one way. I could convert it into XYZ coordinates, and then I could use a three-dimensional convnet to recognize if there's a person. And so what did I just do? I went through some of these scenarios. I want you to not know about convnets and use them, but I want you to think about what convnets do for you. What is the idea behind convnets? And the idea is really we're trying to approximate this thing that is incredibly hard to approximate, that the world has this property that in a way, locally, it means the same thing. Therefore, we can locally extract these things and put them together. And max pool's not quite right, but we don't have anything better. That's why we use it. And so with that, all I can say is this is the last slide. Thanks for coming. And I look forward to seeing you next week. Hey, one second. I'm trying to. I need to stop. What? See ya. Gosh, Zoom.